we look at limits of functions of several variables. Limits of functions of several variables. Now let's define the distance between 2 points. Now if we have 2 points P and A, the distance between P and A denoted P A is equal to the square root of summing xi minus ai all squared. Here I running from 1 to n. An example is, let's take the point P to be equal to x1, y1, x1, x2, and x3. And let's take the point A to be equal to A1, A2, and A3. Then we say that distance between P and A denoted that is equal to, here is the square root of x1 minus a1 all squared plus x2 minus a2 all squared plus x3 minus a3 all squared. That will give us the distance between the 2 points A, P, and A. Okay, now we define if P minus the distance between P and A is less than R. We call this one here an open ball. And this distance between P and A, if it's less or equal to R, where here R is a real number, any number at all, then we'll call this one here a closed ball. Okay. Now, what is limit of a function? Limit of a function. Okay. Now, the limit as P approaches A, f of P is equal to L. If for any epsilon greater than 0, any epsilon greater than 0, there exists some delta which is a function of epsilon also greater than 0, such that if the distance between the point P and A is between 0 and delta, then f of P minus L is less than epsilon. It's less than epsilon. Now this is the classical definition of limit. Let me take this again. The limit as f of p approaches a of f of p is equal to L if and only if for any epsilon greater than 0, however small, there exists a delta of epsilon also greater than 0, such that if the distance between the points P and the point A is between 0 and delta, then the absolute f of p minus L is less than epsilon. Okay, we look at some properties of limits. We would come back and we'll expand the definition later. Okay? If the limit as p approaches a of f of p is equal to L1 and limit as p approaches a, g of p is equal to L2, then we say that 1 limit as p approaches a of into brackets c times f of p. Let me use the square brackets, please. Is equal to c times L1. And number 2, we say that limit as p approaches a of f of p plus g of p is equal to L1 plus L2. And next, we say that limit as p approaches a of f of p multiplying g of p is equal to L1 multiplying L2. So this is, or these are some properties of limits. Okay. Next, we define an accumulation point. If a point P0 is an accumulation point of a set S of points in Rn, if every open ball contains infinitely many points of X, then that point P is called an accumulation point. Point P is called an accumulation point. Okay. Theorem. Now suppose that a function f is defined for all points on a disk having center A except possibly at A itself, and limits as p approaches A, f of p is equal to L. Then if S is any set of points in Rn having A as an accumulation point, then the limits as p approaches A, where here p belongs to the set S exists of f of p exists and always has the value of L. Okay, now I would break this for you quickly. Okay, now let's say the accumulation point theory states that here I find the limit as p approaches a, right? P approaches a. Now, if that limit exists and is equal to L, then the limit must exist along all the lines that pass through the point A, and it must also be equal to L. An example, quick example. Now, let's look at limit as xy approaches 0, 0 of f of x, y, and let's say this is equal to L. Now, if this is true, that the limit is equal to L, then accumulation point theory states that then limits along all the lines that pass through the point 0, 0 of this same function must also be equal to L. Now, what are some of the points that pass through the point 0, 0? Excuse me for a moment, I'm coming. Yes, sir. Yes, sir. Yes, sir. Alex, okay. Okay, thank you. I'll get back to you. Eh? Thank you. Bye. Okay, now let's look at some of the lines that pass through the point 0, 0. The line curve y is equal to x squared pass through the point 0, 0. Y is equal to x also pass through the point 0, 0. Here we maintain here is x and here is y. The line y is equal to 0, which is the x-axis also pass through the point 0, 0. And the line x is also equal to 0, also pass through the point 0, 0. Now there are lots and lots and lots of lines. Even sine x will also pass through the point 0, 0. So accumulation point theorem says that if the limit exists, then the limit along all the lines that pass through that point must also be equal to the original limits. Okay, let's see what we can do here.